Hello there, we're students from University of Petronas, currently taking a Bachelor's of Chemical Engineering. We're presenting for our Engineering Maths course with the course code FFM1013/FEM1012, creating a lecture video teaching Stokes Theorem. My name is Sri, and after this we'll have Abdul Rahman as well as Adam Haris to present their respective parts. And these are our team members that just complete our project. And then we're done with the pleasantries, let's move on to the introduction of our topic today. What is Stokes Theorem? Stokes theorem relates the line integral around a closed curve can be a loop, a circle, a heart, a flower, as long as the two ends meet and form a loop. To the surface integral of the curve over any surface bounded by the curve using the formula. So what this means is that our curve, when it forms a loop, it will then form a surface. Like for example, a circle, when it's completed, it will form a what do you call it? Maybe like you can say a donut, something like that. Yeah. So then in our formula, we can see that we are curling our vector field function, and then we are also integrating either in terms of S and in terms of A, depends on the variation that we're using. We dissect our formula one by one later using this figure. So the figure here, as you can see, the vector field function F is moving around. This is the blue arrows are our F. So this F is moving around our surface that is formed by the curve. And on this surface, there's unit number vectors, but there are the perpendicular components of our surface. So why are we curling our function in the formula? So we are curling the function because the curve measures how much of vector field rotates around a point. So let's say at this point, how much it's rotating at one point. Now, when it comes to Stokes theorem, when we dot product our curve with either vector field function or the z minus fxy, we are seeing how it rotates around our surface. Okay, so now if you notice, we have two different relations of Stokes theorem, one with normal vectors, one with z minus fxy. Why? Because unit normal vectors are over here. They are the perpendicular components, and they are directly on our surface. However, more often than not, we can't use them because our surface isn't completely flat. Now, why? Because when our unit normal vectors, we're going to use 0, 0, 1. Okay, what I mean by that, you see, 0, 0, 1. It means that our surface here, we are assuming that it is completely flat, and the shadow projected by it, the shadow over here, it has the same area as the surface. But in this case, as you can see, it is not. We have curves here and everything else, but you'll see, if you can visualize, the shadow projected, the area projected will be either a circle or a square, which the area isn't the same at all. Now over here you can see it's almost forming a bell pepper, but over here it's just a circle, a disc. So since it's like that, when our surface is completely flat, we use our unit normal vector. Otherwise, we use z minus fxy to compensate for the curves, because our shadow is a flat disc. It's a flat disc, it's just flat. So we need to incorporate the curves somehow, which is why we are multiplying this with our gradient. Okay, so that is why you will realize that when using unit normal vectors, you're integrating to S because our vectors are on the surface. However, for z minus fxy, it is the area of the shadow. Added in the curves. Yeah, so both are the same, but it's just how and when we're going to be using it. So let's move on to the steps in solving Stokes. Always call your function first. You see the detailed working later. Then after that, you determine which to use, n or z minus fxy, as the conditions I told you just now. When it's completely flat, use n. Other than that, use z minus fxy. Or if in the question it provides you with z in terms of x and y, and for example, z equals to 1 minus x plus 1, then you have to use z minus fxy, regardless of whether the surface is completely flat or not. Okay. After that, find your limits. How do you find your limits? It can be either polar or x and y variables. You will know that the model is in polar form because of the circle equation. X squared plus y squared equals to r squared. Maybe your r squared can be 16. Means your range of your radius can be from 0 to 4. And your data by default, unless stated, will be 0 to 2 pi because it's a full circle. Okay, so that's for polar. When if you see x squared plus y squared, automatically polar. But if not, you have to find the limits for your x and y variables, which, if you remember our previous lectures, we can use the type 1 and type 2 region methods. The vertical and the horizontal methods to determine our upper and lower limit base. I mean, if you do remember, this is how it's going to be. The above will be upper, the below lower, right. I mean, the right is upper and left lower. After determining the limits, calculate using your Stokes formula, either with S or 8, depending on which formula you decide to use. After that, the answer is achieved and we are done. So that's the introduction and the steps in solving Stokes. Let's move on to the example problems with Abdurrahman explaining them.
Okay, so for the question 1, we'll be using Stokes theorem to evaluate f integral of f, the derivative of r, where c is the circle x squared plus y squared is equal to 16, and z is equal to 5, oriented counterclockwise, and f x y z is equal to y z I plus 2x z j plus e of x raised to y, e of e raised to x y. Okay. Here we will be using, first we begin the problem. Our curve is the circle of radius 4 in the plane z is equal to 5. And our step will be to choose a surface. The simple surface bounded by the circle is the flat horizontal disk inside it. This is our understanding. The curve is oriented counterclockwise. Using right-hand rule, we can find out that the unit normal vector n for our disk is straight up, which is n is equal to 0, 0, 1. Why? Because our equation is etc. represents a flat disk. Moreover, z is equal to phi, meaning that the disk is elevated by phi units. Okay, next we compute the curl of f. Our vector field is f is equal to yzi plus 2xzj plus e raised to xyk. So using our formula, the curl f is the gradient into cross product of f vector. So after the cross product, we get this, and later on we set up the surface integral to equate the curl dotted with the normal, and we get the answer as x e raised to xy minus 2x y minus ye raised to xy and z. Okay, so given this, we get this graph, and where this is the cylinder and surface, which you can see with 4 radius when z is equal to phi. And setting up the integral, we integrate the curl of f vector dot product. Here we use dot product into the n of derivative of a. So, and using the area of circle formula, we get that using the radius as 4, we can substitute it inside to get the answer as 85. Okay. Okay, question number 3. Okay, use Stokes theorem to evaluate integral of f dot dr, where fxyz is equal to 3zi plus 4xj plus 2yk, and c is the boundary of the paraboloid z is equal to 1 minus x squared minus y squared, for which z is greater than or equal to 0 with upward orientation. All right, for this question, we will be using the surface and the normal. We again use the flat disk. The orientation for this will give us the dome-like region for S, and the normal will yet again be 0, 0, and 1. Okay, first we compute the curl using the same formula, gradient cross product of f vector. And here we assume z is equal to 1 and x is equal to plus or minus 1 and y is equal to plus or minus 1 given from the equation. And we get the answer as for this. And then in using the figure, we can find the intercepts, and the paraboloid is equal to curved lines. And for the circle region, we get x squared plus y squared is equal to 1 and z is equal to 0. For here, we know that the area of S is not equal to area of R. So we can now use the integral for the calculation to find the curl. All right. So setting up the integral, we multiply the gradient into the Z minus f of xy. And therefore, we get the answer for this, which we substitute into the integral, and we can continue on to find the answer is 4 pi. Okay, moving on, we will be using the Stokes theorem to compute the integral of f dot dr. F of xyz is equal to x squared zi plus xy squared j plus z squared k, and c is the curve of intersection of the plane x plus y plus z is equal to 1, and the cylinder x squared plus y squared is equal to 9 as viewed from above. Again, we need to find the curl, and here we use the same formula to find out this 0, x squared, and y squared. And then we multiply the curl, the gradient, with the z minus f of xy to get 1, 1, 1. Here, the figure shows the region where z is equal to 1 and x squared plus y squared is equal to 9. Continuing on the question, we multiply the curl of f vector f into the gradient of z minus f of xy, and we get the limits for this, the upper and the lower ones. So we can put it into the integration, and when we integrate, we find the answer as 81 by 2 pi. That's all from me. We will now be moving on to the real-world problem identification.
How do I stop recording first?
Now we move on into the real-world problem identifications using Stokes theorems. Now, for example that I'll be using is an aeronautical engineer that needs to calculate the lift generated by an aircraft wing. As in the picture, we can see there are two regions of air flowing, which is at the upper part of the wing and the lower part of the wing. So the air flowing around the wings, for each of the air has a known velocity field. It is also observed that the flow is faster over the top surface and slower under the bottom surface, that creates a circulation of air around the wing. Next slide, please. Sorry, next slide. So the Stokes theorems lets you measure how much the air is swirling around the whole wing by instead adding up the tiny mini swirls, vortices inside the air surrounding the wing. So it explains that each of the region of the air flowing has its own mini swirls, as we call as vortices, and the Stokes theorems lets us to calculate the whole region circulating the uh, plane wings, that are overall vortices. So the problem is it is hard to track the air's push along the wing's complete shape. So instead, we measure the net spinning motion, the total vorticity at the border of the plane wings. So the bottom line is the total swirl around the wing equals to the sum of all mini swirls inside the area. So this information is crucial because those mini swirls are what create the pressure difference, which is the fast low pressure air on top and slow high pressure air below, that helps the plane fly. So Stokes theorem connects the large scale lift to the small scale spinning in the air. So that's all for the real world problem identification for the Stokes theorems.